Good morning, welcome to Optical Communication video lecture series. In this class, we are going to learn about historical development of optical fiber communications, where we are going to learn about different stages that have been involved in the development of optical communications. By the end of the session, you will be able to learn about different generations that the optical fiber communications have undergone till today. And then in those different generations, what are the different bit rates that we have used and what are the different wavelengths that we have used in each and every generation, and what is the development that it have undergone from one generation to another generation. Coming to the introduction, historical development consists of fiber optics that deals with the study of propagation of light through transparent dielectric wavelengths. That means fiber optics in general deals with the study of propagation of light, that is movement of light through a transparent, that means a medium which is going to allow light to pass through it, and it is dielectric. That means it is not going to conduct any electrical charges. And finally, we call it as wavelet because it is going to guide the waves through it. Okay. The fiber optics are used for transmission of data from one point to another point. That means fiber optic is used for transmitting data from the transmitter to receiver. Each point, one point is your transmitter and the other point is your receiver. Fiber optic systems are used most extensively as the transmission line between terrestrial and hardwired systems. That means fiber optics are most widely used on the terrestrial landscape systems and for hardware systems. That means fiber optics deals with your wirings and with the systems that are connected with wires. It is not a wireless communication system. The carrier frequency used in conventional systems had the limitations in handling the volume and the data rate of the transmission. That means before going for fiber optic communication system, we used to have general electrical model where we used to go with coaxial cables for transmitting data. In that case, the limitation is in terms of volume. That means you can't transfer large amount of volume or you can't transfer data at high speed. So in order to avoid these two limitations, we went for fiber optic communication system. The greater the carrier frequency, larger the availability of bandwidth and information carrying capacity. That means as the carrier frequency increases, its ability to carry the information also increases because since bandwidth is increasing, due to the increase in the frequency, we know that bandwidth is 2 times of your frequency. So since the frequency is increasing, bandwidth is obviously increasing. As the bandwidth is increasing, it allows more information to pass through it. Thus, we are increasing the information carrying capability. Coming to the first generation of light wave systems uses gallium arsenide semiconductor laser. So here, the transmitter that is being used is gallium arsenide, which is an extrinsic material. The bitrate achieved in first generation is 45 megabits per second, and the repeater spacing is 10 kilometer apart. That means for every 10 kilometers, there is a need for repeater. What do you mean by repeater? A repeater is the device which is going to receive the incoming signal, and then it is going to apply three modifications. One is timing, the other one is shaping, and the other one is amplitude. That means if the amplitude is less, the repeater is going to increase the amplitude. If the timing of the signal is varied when compared to the input signal, then it is going to readjust the timing. And then final one is shape. If the beam is in dispersive in nature, when it comes to the repeater, it is going to make a perfect shape again, and then it is going to transmit to other receiver repeater. The wavelength used is 0.8 micrometers, that is 800 nanometer wavelength. So in the first generation, we have used 800 nanometer wavelength, and the bitrate that we have achieved is 45 Mbps per second. Mbps. Repeater spacing is around 10 kilometers. That is, for every 10 kilometers, there is a requirement of repeater. When we went for the second generation, the speed is increasing. That means it became 100 Mbps to 1.7 Gbps, and the repeater spacing is also increasing. That means we need less number of repeaters when compared to first generation optical communication. That means by how much value? By 5 times. We can reduce our repeaters by 5 times. Here we can place one repeater at one point and the other repeater can be placed at 50 kilometers apart from this. Okay. Next, the operating wavelength is varied. That means it became 1.2 micrometers. And the semiconductor laser, which is used for transmitting, is indium gallium arsenide phosphide. Okay. Third generation. Coming to the third generation, the development is in terms of bit rate. That is, it became 10 Gbps when compared to the second generation. Repeater spacing became double. That is, in second generation, we have used each repeater at a distance of 100 kilometers, 50 kilometers. Here we are using each repeater at a spacing of 100 kilometers. That means we are reducing our repeaters. And coming to operating wavelength, we are using a wavelength of 1.55 micrometers. Coming to the fourth generation uses wave division multiplexing technique. That means we are going to divide our waves and we are going to use multiplexing techniques. That means we are going to utilize our space which is available more conveniently. Here the bitrate became 10 Mbps. Okay, that means we can send more amount of data at a high speed when compared to your third generation. This is made possible by your WDM technique, that is wave division multiplexing technique. That means we are going to transmit different waves at a time, but we are going to use a multiplexer which is going to give one wavelength at the output at a time. So by increasing the input wavelengths, we are increasing the data. So now coming to the repeater spacing, here we can place each repeater at a distance of 10,000 kilometers or more. Coming to the operating wavelength, here we are again trying to reduce our operating wavelength. It lies between 1.45 to 1.62 micrometers. Then comes fifth generation optical fiber communication system. In the fifth generation optical fiber communication system, Raman amplification technique is used and optical solitaires are used. Here the bitrate is increased to 40 to 160 GB per second. Since we are amplifying whatever data that is transmitting. Since amplification is done, our repeating spacings are also increasing. Here we are multiplying that repeater spacing by 2.4 times. That means in the previous case we have used each repeater at a distance of 10,000 kilometers. In this case, we are placing each repeater at a minimum distance of 24,000 kilometers. And the operating wavelength became 1.53 to 1.57 micrometers. And then comes what are the major milestones in electrical communication. In 1838, Samuel F.B. Morse invented telegraphy, where we used to send information using symbols. And then in 1866, first transatlantic telegraphic cable has been introduced for transmitting data. And then in 1876, Alexander Graham Bell invented telephone, through which we can send our voice signals. And then 1905, diode-based electronic amplifier. In 1940, first coaxial cable system has been introduced for transmitting voice channels easily. In 1948, we went for our first microwave system. Why we went for first microwave system? Here, the frequency is increased from 3 megahertz to 4 gigahertz. In 1975, again, the most advanced coaxial system with a bitrate of 274 Mbps per second, MB per second has been developed. You can see that in the graph. First, we went for telegraphy, where we can send only symbols, and then we went for telephone, where we can transmit voice signals, and then we went for coaxial cables, where we can make the communication through radio signals. Okay, and then we went for optical fiber. In optical fibers, in order to increase the data rate further, we went for WDM, wave division multiplexing techniques. And this wave division multiplexing technique had been introduced in the year 2000. Now, coming to different symbols that we have on, optical communication system of the 20th century is wire telegraphy. Two wires for telegraphy transmission, that is simplex and duplex. So simplex and duplex are used for two-way communication. Duplex is used for two-way communication. Simplex is for only one-way communication. Wire telephony, two wires for telephone transmission of one channel. Here we use only single channel. Okay, but we are using two wires in the single channel. Then came carrier telephone. Carrier telephone is for long distance telephone using different channels, that is 4, 8, and 16. That means we can use 4 channels, 8 channels, and 16. Coming to coaxial cable system, for 32 channel PCM system. So you can observe that in the figure there is a coaxial cable system that is shown. Here we can transmit up to 32 channels. Using 32 channels, we can transmit information in this system. And and the bit rate we have achieved is 2.048 MB per second. Problems on electrical communication system. What are the problems that you will have encountered while using electrical communication system? That is, electrical communication system is affected by EMI, electromagnetic interference. That means atmospheric interferences are more in electrical signal. Since the signal is electrical, outer electrical energy used to change modifications to the information which is being transmitted to your cable. And the bandwidth is low when compared to your optical signals. That is around 4 kilohertz per telephone and 100 megahertz per coaxial cable. High attenuation. Attenuation is very high. That means we need to give more power at the input side, which is going to increase the cost. High system cost due to too many repeaters for a given bandwidth or data rate. We are using too many repeaters in coaxial communication system. Here, 32 channels PCM link required one repeater every 2 kilometers. This is easily prone to tapping. That means we can tap information at any point by cutting the coaxial cable and connecting a receiver. Anybody can tap the signal and listen the information which is being transmitted. And coaxial cable system is very bulky. History of optical fiber communication systems. In 1966, suggestion to use optical fiber is made by Cavo and Cam. They suggested to use an optical fiber communication in order to reduce the bulkiness and reduce the weight. Okay. In 1970, Corning glass optical fiber with 20 dB per kilometer near 1 micrometer is made. Here 20 dB per kilometer is the loss that is achieved by an optical fiber when information is being transmitted. For every 1 kilometer, there is a loss of 20 dB, and the wavelength is 1 micrometer. And then we went for 1978 again, semiconductor laser with continuous wave operation at room temperature. That means we have designed a semiconductor laser to transmit the information to use as a source. In 1980 onwards, widespread use of optical fiber communication using SMF and multimode fiber model. Single mode fiber and multi-mode fiber have been introduced in 1980. We will be learning about single mode and multi-mode fibers in later classes in detail. Okay. 1990. In 1990, optical amplification is introduced for increasing the repeater spacing. Since amplification is done, repeaters are placed at large distance when compared to the previous case. That is how we are increased our repeater spacing. Wavelength division multiplexing is used for increasing data rate. That is, we can send different wavelengths at a time, but we can take only one wavelength at a time, resulted in data rate to go for 10 TB per second by the year 2001. Advantages that we can have if we use optical fiber communication, that is fiber optics. Bandwidth will be high, that we have seen in earlier slides. Very low attenuation, since you can observe in this slide that the attenuation is around 20 dB per kilometer in 1970. By 2000, we reduced it to 0.16. How did we attain that? We attained that using efficient transmitting sources and then by using single mode and multi-mode fibers. Okay, and then through amplifications. Immune to EMI. Here, electromagnetic immunity is provided since the conductors are dielectric in nature and the information is traveling in the form of light, not in the form of electrical energy. Data security, almost impossible to tap for information because it is light information. If you break the optical fiber, it is going to have many dispersions and all the information can't be tapped by the returners. If somebody want to take the information from your cable, it is impossible. So we are providing data security. Hence, we can use it in military applications. Lower system cost, fewer repeaters due to attenuation of the fiber. Since we are using less number of attenuators, the system cost is small size and low weight. If the size of optical fiber, we can observe here, optical fiber sizes are very small, so their weight is also small. Very low bit error rate. Here, the error rate is low. That is, our attenuation is low, so error rate is also very low. Okay. Here, the terms that we need to learn is WDM, wavelength division multiplexing, LED emitting diodes, PCM, pulse code modulation that we have came through. And then SMF is your single mode fiber, MMF is your multi-mode fibers. Okay, these are the different technical terms that we have came across this. Okay, in the next presentation, we are going to learn about the block diagram of an optical